Hello everyone, this is Vatsalya and I'm going to talk about the differences between point coordination function and distributed coordination function. To understand the coordination functions, let us talk about the IEEE 802.11 MAC layer. It covers three functional areas: reliable data delivery, access control, and security. For access control, two types of protocols were considered: distributed access protocols and centralized access protocols. Distributed access protocols are mainly used for ad hoc networks that consist primarily of peer workstations and other wireless LAN configurations with bursty traffic. A centralized access protocol is natural for configurations in which a number of wireless stations are interconnected with each other and some sort of base station that attaches to a backbone wired LAN. It is especially useful if some of the data is time sensitive or of high priority. The end result for 802.11 is a MAC algorithm called DFW-MAC, Distributed Foundation Wireless MAC, that provides a distributed access control mechanism with an optional centralized control built on top of that. In this figure, we can observe that the lower sublayer of the MAC layer is the distributed coordination function. DCF uses a contention algorithm to provide access to all traffic. Ordinary asynchronous traffic directly uses DCF. The point coordination function is a centralized MAC algorithm used to provide contention-free service. PCF is built on top of DCF and exploits features of DCF to assure access for its users. As I have mentioned, DCF or contention service is good for ad hoc networks. PCF, on the other hand, is good for wireless LANs connected to a backbone. Let us talk about the distributed coordination function. The DCF sublayer makes use of a simple CSMA, that is carrier sense multiple access algorithm. If a station has a MAC frame to transmit, it listens to the medium. If the medium is idle, the station may transmit. Otherwise, the station must wait until the current transmission is complete before transmitting. The DCF does not include a collision detection function because collision detection is practically not possible on a wireless network. The dynamic range of the signals on the medium are very large so that a transmitting station cannot effectively distinguish incoming weak signals from noise and the effects of its own transmission. To ensure the smooth and fair functioning of this algorithm, DCF uses a set of delays that amounts to a priority scheme. Let us consider a single delay known as interframe space. We will talk about the different types of delays later on. This is how the medium access control logic works. A station with a frame to transmit senses the medium. If the medium is idle, it waits to see if the medium remains idle for a time equal to IFS, that is the interframe space. If so, the station may transmit immediately. If the medium is busy, the station defers transmission and continues to monitor the medium until the current transmission is over. Once the current transmission is over, the station delays another IFS. If the medium remains idle for this period, then the station backs off a random amount of time and again senses the medium. If the medium is still idle, the station may transmit. During the back-off time, if the medium becomes busy, the back-off timer is halted and resumes when the medium becomes idle. To ensure that the backoff maintains stability, binary exponential backoff is used. Binary exponential backoff provides a means of handling a heavy load. Repeated failed attempts to transmit result in longer and longer backoff times, which helps to smooth out the load. Without such a backoff, two or more stations may attempt to transmit at the same time, causing a collision. These stations then immediately attempt to retransmit, causing a new collision. Now let us talk about the interframe spaces. There are three types: SIFS, PIFS, and DIFS. SIFS stands for Short IFS. It is the shortest IFS used for all immediate response actions. For example, acknowledgement. When a station receives a frame addressed only to itself, it responds with an ACK frame after waiting only for an SIFS gap. Clear to send. A station can ensure that its data frame will get through by first issuing a small request to send frame. The station to which this frame is addressed should immediately respond with a CTS frame, and this is done after waiting for a time equal to SIFS. PIFS is a mid-length IFS used by the centralized controller in the PCF scheme when issuing poles. DIFS, or the Distributed Coordination Function IFS, the longest IFS, which is used as a minimum delay for asynchronous frames contending for access. PCF is an alternative access method implemented on top of the DCF. The operation consists of polling by the centralized polling master or the point coordinator. The point coordinator makes use of PIFS when issuing polls. Because PIFS is smaller than DIFS, the point coordinator can seize the medium and log out all asynchronous traffic while it issues polls and receives responses. As an extreme, consider a scenario. A wireless network is configured so that a number of stations with time-sensitive traffic are controlled by the point coordinator while remaining traffic contends for access using CSMA. The point coordinator could issue polls in a round-robin fashion to all stations configured for polling. When a poll is issued, a poll station may respond using SIFS. If the point coordinator receives a response, it issues another poll using PIFS. If no response is received during the expected turnaround time, the coordinator issues another poll. If the discipline of the previously mentioned scenario were implemented, the point coordinator would lock out all asynchronous traffic by repeatedly issuing polls. To prevent this, an interval known as the superframe is defined. During the first part of this interval, the point coordinator issues polls in a round-robin fashion to all stations configured for polling. The point coordinator then idles for the remainder of the superframe, allowing a contention period for asynchronous access. The figure illustrates the use of the superframe. At the beginning of the superframe, the point coordinator may optionally seize control and issue polls for a given period of time. The interval varies because of the variable frame size issued by responding stations. The remainder of the superframe is available for contention-based access. At the end of the superframe interval, the point coordinator contends for access to the medium using PIFS. If the medium is idle, the point coordinator gains immediate access and a full superframe period follows. However, the medium may be busy at the end of a superframe. In this case, the point coordinator must wait until the medium is idle to gain access. This results in a foreshortened superframe period for the next cycle. To sum up, the 802.11 medium access control protocols are of two types: distributed access protocols, which, like Ethernet, distribute the decision to transmit over all the nodes, including a carrier sense mechanism, and centralized access protocols, which involve regulation of transmission by a centralized decision maker. A distributed protocol makes sense for an ad hoc network of peer workstations and may also be attractive in other wireless LAN configuration that consists primarily of bursty traffic, whereas a centralized access protocol is natural for configurations in which a number of wireless stations are interconnected with each other and some sort of base station that attaches to a backbone wired LAN. It is used if some sort of data is time sensitive or of high priority. DCF provides contention service while PCF provides a contention-free service. DCF operates in the lower layer of the MAC and PCF operates in the upper sublayer of the MAC layer. Thank you.